So in previous lecture we run the first recursion style called return based recursion. Okay, so what's the idea of first style recursion? Small answer, my work, and final answer. So in return based recursion, every function says give me the smaller answer first, then I will do my work and return the final answer. Okay, let's see. I will take repeat 1 2 3. So smaller answer means 2 3 3 and empty subset. Okay, every function trusts the recursive call. So every so can every recursion problem be solved using exactly the same thinking? No. Okay, so recursion is one concept, but there are different ways to think it. Okay, so this is the style 1 return based recursion. Return based recursion is a style 1, and today we are going to learn style 2. Okay, that was include exclude backtracking. Okay, so today we will run the second style include exclude backtracking, and we are going to solve the same LeetCode problem again. That was 78 LeetCode problem. Okay, so and we solve this problem only. But wait, we already solved this problem, then why solve it again? Because the answers stay the same, the recursion changed, the thinking changed. So what's the biggest difference? So in style 1 we get the smaller answer. In style 2 we make decisions. Okay, in style 2 we make decisions. So this is the biggest difference. In return based recursion I say give me the smaller answer, but in backtracking we never ask anyone for an answer. Okay, instead I make decisions myself. Before we run style 2, let's understand one word, that was backtracking. So now what is backtracking? The word backtracking is made of two parts. Okay, so the word of backtracking, that's made of two parts, that was back plus tracking. Okay, back means back only, so we know that. Okay, tracking means finding your path. Okay, and now what is a path? Tracking means finding a path. So what is meant by path? So path is the journey from the start to your current position. Okay, so see, imagine you are drawing a house. Okay, first you draw the roof, then first you have draw the roof. Okay, roof, then you draw the door, then you draw the door. Okay, after looking at it you realize the door is too big, so this door is too big. So can you continue drawing the window? No. So first you erase the door. First I erase the door because the door is too big. Okay, so then you draw a small door. So then continue drawing. So what happened? You made a choice. Okay, I have made a choice. I have erased the big door and I make a small door. So I have make a choice. So this, yeah, I have realized it was not the one I want. So I went back, undid my previous work and tried another choice. Okay, let me explain you one more time. See, imagine you are drawing a roof, then you draw the door. So after looking at it you realize the door is too big. Okay, so the door is too big, so you cannot continue to draw the window. First you erase this door. First you erase this big door, then you draw a small door. So then you continue drawing. What happened? You made a choice here. Okay, you realize it was not the one you want, so you went back, you undid your previous work and tried another choice. So that is a backtracking. Okay, see, okay, let's take one more example. Suppose you like drawing, so you like, first you have write you like football. Okay, in paper you have write football, you like football. Then you think, no, I want to write about coding. So you erase this football, you erase that football, and you like, I like coding, you write this. Okay, what did you do? You went back to your previous decisions and change it, so that is also backtracking. So simply backtracking is a technique where we make a choice, explore that choice completely, and undo that choice, and then explore the next possibility. Okay, so see, simple backtracking means choice, explore, undo, and explore again. Okay, so now what is meant by undo? See, undo, before we continue, let's understand one word, that was undo. Okay, so undo is, see, simply undo means simply to cancel or remove your last action and go back to the previous stage. Okay, so I like football. So then I realize actually I want to write coding. So what you erase the football. Now you write I like coding, you erase this football. Okay, and you like, I like coding. So see what happened, you remove your previous action. Okay, so this is called undo, same like backtracking only. Okay, imagine you are drawing a simply smiley face. Okay, smiley face, I'm drawing, imagine you are drawing a smiley face. Next, first you draw a big eyes, then you think, so see, then you think the eyes are too big, so you erase them. Okay, you erase that big eyes. You think the eyes are too big, so you erase them, then you draw a smaller eyes. Okay, you removed your previous drawing before trying a new, that is undo. Okay, you have removed your previous drawing before you try a new one, so that is called undo. Undo means go back to how things we are before your last decisions. Okay, backtracking also follow the same cycle. That's it. Okay, see, CHOOSE, choice, make our decisions. Okay, then XPLORE, explore, follow the decisions completely, then undo, remove your last decisions, then choose another option. Okay, means explore the remaining possibility. Okay, backtracking is impossible without undo. If we do not undo our previous choice, we cannot explore the next choice correctly. So see, now we know two important things, what is backtracking and what those undo means. Okay, so how do we use backtracking in recursion? Okay, that's exactly what style 2 teach us. So see, in the previous lecture we have run return based recursion. It says smaller answer, my work, and final answer. Every function used to say give me the smaller answer first, then I will build my answer. So but in style 2 things differently, because backtracking does not ask for a smaller answer. Instead it says I will make my own decisions. This is the biggest difference. Okay, so what in so backtracking says I will make my own decision, so that was biggest difference. So now what is called include, EXCLUD, exclude. Okay, because of every element we always ask the same question, include and exclude. So what, see, that's why this style is called include exclude backtracking. Okay, another way to say it, you can also call them include means take, exclude means skip. Okay, that means exactly the same thing. Okay, include means take, exclude means skip. So let's understand with a very small example. 1 2. Okay, so we want to generate all subset of this array. Before making any decisions, have we picked any element? No, we have not picked 1, we have not picked 2. So currently our subset is empty. Okay, so see, does not mean the answer is finished. Okay, so simply it represent our current state. Okay, so right now we have not chosen anything here, then start. So this is the root of our recursion tree. So see, it represents the starting point. At the beginning our current subset is empty because we have not made any decisions yet. So now I stand at 1. So I am standing at the first element, which is 1. So what can I do with 1? I only two choices. I do not take it or I take it. Okay, include or exclude. But see, now we build. First we go to the left. If I skip 1, I am adding anything to the subset? No, I am skipping. So my current subset is still empty. Okay, I have skipped 1. Then see, now the right branch. If what I include 1, if what I take 1, now I had 1 into my subset, so current subset become like this. Okay, so this branch different because I chose to include 1. See here, the tree is not storing answer, the tree is showing the current state after every decisions. Okay, left side is empty, I have skipped 1, and right side I have take 1. Okay, so I include 1. Every node in the recursion tree represent the current subset after decision we have made so far. Okay, now see, current subset is this. Now we have made decisions for 1. Now let move to the next element, which is 2. Okay, so now I am standing at 2. Again I have two same choice, if I to skip 2 or take 2. Okay, the question never change. For every element we always ask include 2 or exclude 2. So now we explore the left side first. So current subset is empty here, so we have two choices. So see, let's first explore the left branch only. Our current subset is still empty because we have skipped 1. Okay, so what if I also skip 2? I have skipped 2 here. Okay, so do we add anything here? No. So the current subset is still empty. Okay, now our tree look like this. So we have processed every element. Now we have processed every element. There are no more there are no more decisions has left, so this become one complete subset. So we store the answer. Okay, now we backtrack. We go back, it remove that. Now we go backtrack here. So see, can I go forward? No, we have reached the end, so recursion return the previous decision, so that is called backtracking. Okay, now explore the another decision. Now see, we already explored skip 2. Okay, now let's explore the another choice, that was take 2. So now current subset look like this. Okay, again we have processed every element, so we store 2 also. Okay, then again we go back, right, we undo this, we come here. Okay, now both choices for 2 are completed, so we go back again. Okay, now our tree look like this. Okay, because we have explored this all. See, now the entire left side is finished, so explore the right side. So that was current subset 1. Now let's explore the right branch. Earlier we include 1, we have take 1, so our current subset is 1. Now we are standing at 2 again. Okay, here and now we are standing for 2 again. See, same question, include 2 or exclude 2. Okay, how it's if I skip 2, so if I take 2, 1 2. Okay, if I exclude 2 means if I skip 2, so it's remain like this. If I take 2, so subset become like this. So the answer is 1 1 2. Okay, so that was right answer. So both reach the end of the array, so both are start. Did you notice something every time we reach an element we ask exactly the same question, take it or skip it. Okay, so every decisions created two branches, every reef become one answer, and after finishing one branch recursion backtrack to explore the remaining branch. Okay, let's take one more example, because undo is the heart of the recursion backtracking. Okay, let's take one more example. So we have array like A, B, C. Okay, so our current subset is empty because we have not taken anything. See, at the beginning I have not choose anything, so my current subset is empty. I am standing at A, so I have two choices. I have only two choices, so skip A or take A. So if I skip A, if I take A, okay, so my tree start like this only. As always we explore the left branch first, so we skip means I do not add A, so my current subset is still, my current subset is, see, my current subset is still empty. Okay, so now tree become like this. Same, I do not add A, so my current subset still empty. Now tree become like this, I have not added A. So I am standing at B. Okay, first let explore left side only. Now I am standing at B. Okay, my subset look like this only. So again I have two choices, skip B or take B. So if I skip B, see, if I skip B, so let me write here, skip A, skip B. Okay, skip B means do not add B, so subset remain this only. Now the array is finished. Let's take two element only, A and B only. Okay, so now the array is finished. Okay, so we have store, and I have explored both choices for B. Did I explore both choices for B, skip and take? No, we have just explored the skip branch. Okay, so see, I only explore skip B, so I still need to explore take B, so I can go directly there. Yes, so because I have added B, so my current subset is already, so we take B, so our subset become like this. Okay, now we have store A, B. So see, now I am done exploring the take branch, so current subset is B, but I want to go back to the parent. Okay, so the parent subset is empty subset, so what should I do? I remove B. Okay, we go backtrack. So this is undo or backtracking, so go back to root. The entire left side is finished. Okay, so now see, now go back to the root, so our tree look like this, okay, so now we have explore. So see, now we take A. Okay, so if I take A, so our subset become like this. Then I am standing at B again. Now I am standing at B again, so it's basically if I skip B or I take B. Okay, skip B or take B, subset, if I skip B, so subset remains same. If I take B, subset become like this. Okay, so full tree look like this, empty subset. First option I skip A, then I take A, then I skip B, then I take B. Here also same, I skip B, then I take B. Okay, so the answer is empty B, A, B. Okay, see, so we have stored AB. So now the biggest question is, current subset is AB. Can I go back to my parents while keeping B inside? No, because the parent subset was A. Okay, so first we have to undo B, then I can go back to the root by keeping A. Okay, then we undo the B, I go back again keeping A. No, because the root subset was empty. Okay, so I undo the A, then I go back. So our tree look like this only. Every node in this tree has its own current subset. Okay, so when we return to parent node, the subset must become exactly the same as it was at that parent. Okay, so see, but why we do undo? Now we understand the idea, but backtracking the but but understanding the idea is not enough. Okay, in recursion and backtracking, the biggest skills is learning how to trace the function calls. That's why we will do one more dry run, and a dry run helps as answer three important question. Okay, where I am right now, what decision I am making, why I am coming backtracking. Okay, if you can dry run recursion, you can write recursion. Okay, so let's trace one more example. Let's take small example only, 2 and 4. So my current subset is empty. Okay, first I am standing at 2. Okay, I am at the first element, which is 2. So ask yourself, how many choices do I have? So the answer is only 2. Skip or take means exclude or include. Okay, so I skip 2. It's look like this. If I take 2, let first always see, as always recursion explore the left branch first. Okay, the left branch first. So what does we skip 2 means? So a subset is still empty. It's look like this only. See, next now we point to 4. So question, how many choices I have? Only 2. Skip 4 or take 4. Okay, skip. See, if I skip 4, what does my subset become? Like this. Okay, if I process my every element, see here, have I processed my every element? Yes, in left side I have processed my every skip element. So what should I do? We store the subset. So the answer is this. Now we backtrack, and have I explored both choices of 4? We do backtrack. Have I explored both choices of 4? No. So see which choice is left, the take. Okay, so I return to the previous decisions. This return is called backtracking only. Okay, see, I have stored the answer, current subset. Have I explored both choices of 4? No, we have just explored the left side, skip. So which choice is left? That is 4. We have to take 4. So I return to the previous decisions. So this, when I have written this previous decision, that only called a backtracking. Okay, so now we take 4. So what happened if I include 4? So our current subset look like this. Okay, no, array has finished. Yes, so we have stored 4. So current subset is 4. Now can I go to the parents by keeping 4? No, because it was empty, so we remove 4. So, okay, so this is undo. We have removed 4, that is undo. Okay, so I am restoring my parents stage. The left side is completely explored. Now return to the root. Okay, this left side is complete. Now we return to the root. So see, if I include 2 na, yes, next what happen if I take 2, include 2? So subset become like this. Now point to 4. Okay, now we see 4. How many choice? Again only 2. Skip 4 or take 4. So if we skip 4, our subset like this only remains same. If we take 4, it's look like this, 2 and 4. Okay, so can I return by keeping 4? No, because my root is, in root there is only 2, so here we undo 2. Okay, 4. Okay, now we return to, can I return to the root by keeping 2? No, because we undo again, because root is empty. Okay, we remove 2 also, this 2 also. Okay, so our tree look like this only. First we remove 2, 4, then we remove 2, undo. sorry. So see, every recursive call follow exactly the same cycle. Look at the current element, take it all, skip it, undo the include, then return to the parents. Every recursive call asks this question: where I am, which element I am processing, what are my two choices, take or skip, what is my current subset, have I reached the end of the array, do I need to undo before exploring another branch. Okay, if you keep asking these 5 questions at every step, recursion and backtracking become much easier to understand. Okay, now let's convert this thinking into code. Now we know the idea. For every element we have only two choices: skip or take. Okay, so let's convert this thinking into code. We will not write the whole code at once, we will write one line, understand why we need it. Okay, 1 minute. Okay, first we need this array. Let's take, okay, see, first we need a array like 1 2. Okay, so see, first we need an input, so it's called an input. Okay, first we need an input, so our input array look like this. So this is the array whose subset we want to find. So while making subset, we will, where will I keep the element that I have already chosen. See, I have choose, for example, empty or 1 or 1 2. So I need one vector to store my current subset. Okay, so we write like this. I want this, wait, first let me write return 0. First we see, first we want input int nums is equal to 1 2. Okay, then we need a vector to store our current subset. This is our current subsets. Okay, that's why we write vector int current. Okay, because we have not chosen anything yet, let me write here, because I have not chosen anything here, so current state like this, see, nums is equal to 1 2, and my current subset look like this. Okay, I have not chosen anything yet, so see, one subset is enough. Where will I store all subsets? So we have to store the all subset, is one subset is enough. So for that we need another vector of result. Okay, we have to store the result also. That's where we write vector and result. Okay, so see, this store every subsets. Now we current vector store every subset, it's look like this. Now we have write result also. Okay, now result is empty. So see, everything is ready. Now who will actually build a subset? So the backtracking function. Okay, everything is ready, where nums of array is ready, current subset and result also is ready. Now who will actually build a subset? So that was a backtracking function. Okay, that's where we write, that's how we write, we need a function. So let me have a notepad. So we need a function, that's why we take, let's write back nums just a minute, nums current subsets and result. I have to write this down. Okay, I'm just showing you, we need this function also. So see, nums means nums nums, I have write nums current subset 0 and result. Okay, nums, next what problem I am solving. Okay, and subset of 1 2, subsets of 1 2. So nums must go current subset and ask what is my current path. Okay, right now it was empty, so current subset goes to 0. Okay, which element I am standing on, current subset is 1 2. So see, index is 0 0 1, index is 0, so we pass 0. Okay, and result, this is result. Where will I store my every subset? So the answer is result. Okay, current state before recursion. So it's look like this. Write clearly. Nums is equal to 1 2, it is index 0 1, current subset is empty array now, and result is empty, and I is equal to 0. Okay, so now let's write the backtracking function, then we understand clearly. So the function is void, because we are not going to return anything, void. Then we have to pass this vector nums. Okay, then we have to pass currents this vector also. Then not 0, we point 0 means index 0. Okay, I, int I, then result. Okay, that's complete. So that's how it's look. Now I am standing here, so I am standing at index 0. Okay, 1 2 0 1, I am standing at index 0. My current number is 1. What's the first thing every recursive function should check? That was base case. Okay, if I is equal to and new nums dot size, so what do we need? So see, why do we need this? See, current is I is equal to 0. So if nums dot size is equal to 2, no. So 0 is equal to 2, index 0 is equal to 2, no. So the answer is no. So the base case is false. Okay, nothing happen. When will it become true? When I is equal to 0, then I is equal to 1, then when I is equal to 2. So 2 is equal to nums dot size. Okay, so no more element has left, no more element are left, so that means one complete subset is ready. Suppose, see, current subset is 1 2. Okay, current subset is 1 2, so the should we throw it away? No, we store it. Okay, so how we store like result dot push back current subset. Okay, current subset. So see, before result is like this, result is empty. Now result is empty. When we do result dot push back 1 2, it's come here. Okay, so then we return. So why we return here? Because there are no more decision left, base case is finished. Now let's write the real backtracking logic. Okay, so let me write the base case. It's complicated. Wait, now it's clear. If I is equal to nums dot size, then push back current subset, then push back current subsets. Okay, and return. return IDURN. So see, this is a base case. This line tell us current subset of final answer we store. Okay, we have store. Okay, our parents function go to the parents function. So let's see what happened in this code. If we run, see nums 1 2, I have right here only. Okay, nums 1 2 and result is empty, subset is like so. Recursion start, how it start, back nums current subset 0 and result. Okay, see this line, nums current subset I is 0 and our result I means our current index. Okay, so now if I is equal to nums dot size, so 0 is equal to 2, no, so the answer is false, so the base case does not run. Okay, so now the function has only one job left. If it has to decide what to do with the current element. Okay, so the current element is 1. Should I skip 1 or take should I skip 1 or should I take 1? This is exactly where the real backtracking logic begins. Okay, see our base case is ready. Now let's write our first decisions. Remember the idea of style 2, for every element skip or take, so we will always explore the skip band first. Okay, so see 1 and concept. So our tree like this is I am standing at 1. If I skip 1, what should my current subset change? Should my current subset change? No, my current subset stays same only. If I skip 1, does it become 1? No. Does it become 2? No. See, if I skip 1, so that's it's become this, no, that's it's become this, no, so it's stay like this only. Okay, so I did not need to change my subset. If I skipped 1, should I keep looking at 1? No. So then where should I go? Next element. Okay, nothing will change, so this simply I have to go just next element. Okay, after skipping next index is 1, so let's write down the skip. See, how can we write? Back nums current subsets I less 1, go to the next element, skip. Okay, ISU result. Okay, see, let me write here and explain you what we have done. Back nums current subset and I plus 1 and result. Okay, so see nums, I am solving another problem. Okay, so I am solving another problem. No, I am still solving subset of 1 2. So nums remaining the same, current subset is empty. Did skip change it? No, so we pass current subset without changing anything, I plus 1. Okay, so current index is 0 1 2, current index is 0 and 1, current element is 1. Okay, so after skipping where should I go? 2, so it's index 1. Okay, 0 1 is index 1, so I plus 1 out of bond. Okay, now result, so where still answer be store, still result. Okay, now see, how can tell you backtrack. See, let me write here. Back nums current subset, current index and result. Okay, if we execute now, how it's look like? Back nums current subset 1 and result. Okay, it's look like this. Notice something, current subset is before recursion, after recursion call, it's same only. Okay, what changed? Only one thing, that was index has changed. Okay, so current state is 1 2, so current subset is this. I is equal to 1, current element is 2. Okay, so we will now standing at 2. Okay, we are now standing at 2. Now how many choices do we have? Skip or take? Again we will explore skip first. Okay, so see, so right now we have finished inside right now we have finished this recursive call. So my current subset like this. So now current value is still 1 2, current subset empty, and I is equal to 1. Okay, so current element is 2 now. So I am now standing at 2. What are my two choices? Skip and take. Just like before, we are exploring skip first. Think first. Okay, you ask yourself, if I skip 2, will my subset change? No. After skipping and before skipping, it stays same only. Okay, nothing changed. Then what should I change? The index, current index. Okay, so what we change? The current index, it comes to. Okay, after skipping, so the same line runs. So this same line, this line runs. Okay, this line runs and call, let me show you here. So it's run, I plus 1, no new call, we back. So that was 2, index 2. So now our tree become like this. Okay, so now something interesting happened. So current is I is equal to 2, I is equal to 2. So is 2 is equal to 2, nums dot size yes. So finally we have reached the base case. So what this means, if I become 2, are there are any element left? No, we have already made a decision of 1, and we have already made a decision of for 2 also. There is nothing left. Now look at our current subset. So see, this is a complete subset. Okay, yes, so this is a complete subset. Yes, should we store it? Yes, we have to store it. That's why we have write this line. Okay, result dot pushback current subset. Now you are getting the point. Okay, in result, where this result is empty now. Where is my result? Oh, where is the result? Now result store this. Okay, so see, can this function make more decisions? No, there are no element left, so we write return only. So this function works is finished. So it now goes back to the function that it called. We have reached our first leaf. Where is our first leaf? We have reached our first leaf. We have stored our first subset. So here we have stored, yes, we will result our first subset also. Okay, we have stored, we have reached a leaf. Now recursion still go back, but when it's go back, it's stop. No, there's still one branch have not explored, that was take 2. Okay, and that exactly what we will do next. We just return from the base case. Here we are going to return. Now I is equal to 1, current subset is empty, current element is 2. Okay, 1 2, current element is 2. Now ask yourself, did you explore both choices of 2? No, we have just skipped and we have to explore the take. So we only explore skip. Now we must explore take. So think first, if I take 2, should my subset change? Now my current subset is this. Okay, if I take 2, my subset will change. Yes, it's become like this. Okay, after taking 2, how do I put 2 into my subset? How do I put 2 into my subset? Okay, see, add it. Let me like, how do I put current subset dot push back nums of I. Okay, nums of I. See, my current subset is this. After executes nums of I, it's become like this. Okay, now our tree look like this. Where is the tree? Okay, what should I do now? Explore the remaining array. If the array, see, are there any element left? No, still we call recursion, okay. So current call, wait, it's look like this. See, back nums current subset I plus 1 and result. Okay, so how it look like? Back, so the nums current subset is 2. Now the I is 2, so result. Okay, I is equal to 2, current subset is 2, so I is equal to 2 base case, so we store this 2 and result we store in result also 2, then we return. Okay, so now the most important movement, see, current function. Okay, see, so my current subset is this. So I am about to go back to my parent. Okay, parent subset was empty, my parent subset was empty, so should my parent receive 2? No. Why? Because parent never choose 2, parent was empty, parent was like this. If we go like this, take 2, everything become wrong. So what should we do? We must remove the last element. Okay, we must remove the last element. We see, what we do undo. Okay, so that's how we write in code, current subset dot pop back. Okay, current subset dot pop back. So that's it. Same see, we have skip and undo because nothing changed, but take change our all subset. So before returning we had to store it also. Okay, that's exactly why every backtracking solution has pushback. Okay, so recursive call and pop back, it's have like this only. See, push back, RECURSIV, recursive call and pop back. Okay, so see, skip, take like this, skip, take, undo and return. Okay, this is the heart of, so this is the heart of backtracking. Okay, whenever you add something before recursion, if you must remove it before returning also. Okay, so let's complete the code. Choice, so this is the choice 1 and this is the choice 2. Okay, current subsets dot push back nums of I. Okay, then we have to explore the next element also. I have to explore the next element also. Okay, then I have to undo back, we have to explore next element, then we do undo. CUR current subsets dot pop back. Okay, let me clear this, let me fix this code. Current subsets, store all subsets, then make call back nums current subsets 0 and result. Okay, let's print them. For auto subsets to result for int x. See, the answer is same. Okay, so this is our style 2 include exclude backtracking code. Okay, include exclude backtracking code. So this line is our first choice, skip the current element. Okay, this will skip a current element. Okay, we have to explore the next element. This line is for explore the next element. This is skip. Wait, let me comment down. This will skip. Okay, back subset I plus 1. Okay, and this line is explore the next element. Okay, explore the next element. This line is no, this will explore the next element. Confusion, command say this line will explore the next element, and this line is include the current element. Okay, this line is okay. Base case return. See, this is the code. It's very easy. Okay, first choice skip the current element. Okay, second choice include the current element. Next is explore the next element. Last we do undo for last choice, so the parent call gets the original subset back. Okay, simple. Okay, so see, last time we have solved this problem return by using return based recursion. That was style 1. So see, so we know that return based recursion, we ask for the smaller answer to solve itself first, and then we build our final answer from it. So today we are going to solve the same problem using completely different way of thinking. So this time we will use the style 2 include exclude backtracking. Okay, so instead of asking a smaller answer, we will make the decision ourselves. For every element we will ask only one question, include exclude, that's it. Okay, so we will explore both choice recovery. See, and after exploring the include branch, we will undo our choice and come back. Okay, so the problem is exactly same we have discussed last time, only the thinking has changed. Last time we have solved it using style 1, so this time we will solve the same problem by using style 2. Okay, so the problem is really simple. We are given array of unique integers, so and our task is to return the all possible subset of this array. Okay, so how we are going to solve it? We are not going to use the return base idea. This time we will use include exclude. Okay, for every element, for every element we will ask only one question: include, exclude. Let's write down the code. So we know the problem. We need a function, copy paste, no, we write, okay, write back vector int nums vector int current subset. We need CURR subset int I and result vector int result. Okay, next a base case: if I is equal to nums dot size, then push result, and when we push result only SULT result dot push back current subset. Okay, so then push back my current subset. Oh, come on, see what happened. Let me write that only. Current SUVSAT. Okay, current subset return it. Okay, next choice 1, exclude the current subset. How we write? Back nums I don't know what happened. Current SUVSAT subset I plus 1 and result. Okay, next choice is take the current element. Take the current element. How we write? Current SUVSAT subset dot push back nums of I. Okay, next explore the next element. How we write? Wait, back nums current SUVSAT subset and I plus 1, then result RSULT result. Okay, then we have to undo the last choice. CURL subset dot pop back. Okay, we have to undo the last choice. Then right, it was complete. Then vector int RSULT result, then current subset VECT eval vector int CURL current SUVSAT subset current subset. So back nums current subset na CURL SUVSAT subset 0 and RSULT result. Okay, in last we are just going to return the result. Return RSULT result. Return result. So that's the code. Okay, see, in return based recursion in return based recursion, time complexity big of n into 2 to the power n, and space complexity is big of n. So in this INCLU extrude the same time complexity. Okay, big of n, this is the time complexity and this is the space complexity. See, in style 1 and style 2 we have the same time complexity and same space complexity. If that complexity is the same, what's the different? The different is not performance, the different is the way we think. Okay, style 1 is return based, smaller answer, my work, and final answer. In style 2, for every element we exclude and include, explore both choice, and then we do undo. Same problem, same complexity, but the different is only thinking. Okay, different is only thinking. See, you may notice that I have explained some ideas many times. So see, my goal is not to make the video longer. My goal is to help you understand every small step. If you already comfortable with recursion, some parts may feel repeated. So but if you are a beginner, this repetition will help you understand the idea much better. Okay, so I do not want to memorize recursion, I want to understand it. Okay, so that's it. Let's run this. Oh, see, the answer is right. Okay, you can see this. Because of network issue it was not running, so the answer is right. Okay.